Hello everyone, we are Group 21 and this is our presentation for our project, Dynamic Object Removing SLAM using MonoRec. I am Janani and my teammates are Yulun, Hao, Jinchao and Vaishnavi. We will first go through the introduction and related works, followed by methodology and look at the results and conclusions. I'll first give a brief introduction of Visual SLAM. Visual SLAM is a technique that allows a mobile robot to navigate through an unknown environment while simultaneously building a map of that environment using visual information from the camera. It involves estimating the camera's position and orientation and mapping the environment based on visual features detected in the scene. Visual SLAM has applications in robotics, autonomous driving, and other fields. But the challenge with Visual SLAM is dynamic objects. Since dynamic objects change position in each frame, they can cause inaccuracies in the tracking and mapping algorithm. The following figures represent the block diagram of Visual SLAM. It mainly consists of dynamic masking system and the tracking system. The input of the dynamic masking system is the RGB frame. The mask module masks out the dynamic object and gives a segmented mask. The segmented mask combined with the RGB frame gives segmented frame from which the dynamic object is removed. This is sent through the tracking module to get the enhanced keyframe which can be used to localize the robot. There have been many attempts made in improving the mask module in previous works to make Visual SLAM more efficient. Now, Jinja will be discussing some of the related works.
There are several related works before. Mask RCNN, which is used in DynaSlime, is a deep learning method for object detection and segmentation in dynamic slime that uses a mask branch. The figure on the right shows the speed performance trade-off for various instance segmentation methods on Coco. We can see that mask RCNN achieves high accuracy, but it's computationally expensive. U-like produces instance masks by linearly combining the prototypes with mask coefficients instead of depending on repooling as mask RCNN. U-like is the first real-time approach with acceptable precision. However, U-like masks both static and dynamic objects. I will hand over Hao.
Okay, so compared with DynaSlam and Yolet, our main contribution is that we propose a method that can prevent the tracking algorithm from using matches that belong to dynamic objects, which leads to, in most cases, we can achieve the highest accuracy in evaluation. At the same time, it prevents the mapping algorithm from including moving objects as part of the 3D map, obtaining a more static map of things. Besides that, we also achieve a great balance between real-time capability and dynamic object masking. And the name of the method we propose is called MonoRec SLAM, where MonoRec just represents a semi-supervised monocular dense reconstruction architecture that predicts depth maps from a single moving camera in dynamic environments. So MonoRec is at first is not designed for a SLAM work, but we find its potential to be used in a SLAM problem. So we adapt that, and the masking module of MonoRec is shown below. The network adapts a UNet architecture design, and the input to that is RGB figures, and the output for that is the dynamic mask for moving objects. For evaluation, we use two different kinds of datasets. The first dataset is Kitty dataset. It's recorded with stereo camera on moving vehicles, and it includes RGB images and a ground truth trajectory. The second dataset we are using is the Tune dataset, and is recorded by an RGBD camera in an office with moving people. The dataset includes RGBD images as well as ground truth trajectories. And I will hand over to Vaish for more discussion about our evaluation on the results.
The two videos on this slide compares the masking performance of MonoRec SLAM and DynaSlam. It can be seen that DynaSlam is masking static objects, which in this case include parked vehicles and smaller buildings. The number of features used for mapping also seem to be lower with DynaSlam as compared to MonoRec, which means DynaSlam considers several of the static objects to be dynamic. Meanwhile, MonoRec does a better job at sensing and masking dynamic objects while placing features correctly on the static objects for mapping. It is evident that MonoRec SLAM performs better than DynaSlam for masking dynamic objects. This slide discusses the APE or absolute post error for MonoRec SLAM and OpSLAM 3 with respect to the ground truth. The graph on the left shows the APE of MonoRec SLAM along the trajectory of the sequence, here KT sequence 7. The red dotted circles highlighted on this graph shows the position on the trajectory at which MonoRec performs significantly better than OpSLAM 3. The graph on the right shows the comparison of APEs for both MonoRec SLAM and OpSLAM 3 with respect to ground truth. The red dotted circles on this figure highlights the time step, around 25 seconds and 85 seconds, at which the APE for MonoRec SLAM is significantly lower than that of OpSLAM 3. At these instances, the frame consists of moving or dynamic objects which are being masked by MonoRec, and therefore the error at these points for MonoRec is low. From the table shown, MonoRec SLAM has the best performance compared to both DynaSlam and OpSLAM 3 for sequences 5 and 7. This is evident from the values of the absolute post error or APE for each algorithm on the given sequence of the KT dataset. While for sequence 0, OpSLAM 3 seems to have the best performance, MonoRec SLAM still performs better than DynaSlam. This slide shows the comparison of computation time in milliseconds for generating masks and tracking poses for MonoRec SLAM and DynaSlam. It is evident that MonoRec SLAM takes about half the time that DynaSlam takes to generate masks and about 1/3 of the time for tracking a pose, enabling it to handle real-time operation. The third column represents the computation time for OpSLAM 3, which is provided for reference. Now I hand it back over to Hao to talk about failure case analysis.
Okay, so though MonoRec works super well with KT dataset, it doesn't work that well with Tune dataset. The right top figure just shows the mask generated from MonoRec on the Tune dataset. You can see that instead of masking the moving people, it's masking randomly on the background. For comparison, the right bottom figure is the mask from mask.cn. We have proposed two possible reasons for that. The first reason is that these two people are too close to the camera, covering too much area. In this case, they are considered as the background instead of the real background, which means the real background is actually considered as the moving object. Another possible reason for that is the two people are just moving too slowly that the MonoRec cannot recognize them. So in conclusion, MonoRec SLAMs achieves in the most cases the highest accuracy on KT dataset and obtains a more static map of things. At the same time, comparing with DynaSlam and YOLACT, MonoRec is the only method that can provide both high accuracy dynamic object masking and real-time operation. For future work, besides improving dynamic masking robustness, we also want to add background in painting functions. We actually have made some trials. The right figure just shows what we get, but the method we tried is called the learning-based flow edge-guided video completion algorithm for background in painting of segmented frame. But this increases the running time to a large extent, disabling it from running real-time operation. Thus, in the future, we will optimize the algorithm to improve its operation speed. Here is the reference page. That's all for our presentation. Thank you for your attention. Now it's for Q&A.